All right, here we are with the solution for one of the practice problems for lesson 4-3. This is going to be the first problem in the practice set. It says a box weighing 77 newtons rests on a table. A rope tied to the box runs vertically upward over a pulley, and a weight is hung from the other end. All right, you can see that in the image that we have here. Determine the force that the table exerts on the box if the weight hanging on the other side of the pulley weighs 30 newtons, 60 newtons, and 90 newtons. All right, so this is a practice problem coming off of our lesson that was heavily focused on free body diagrams. So really quickly, what I'm going to do is I'm going to set up a simple free body diagram for this scenario. What we're going to have is we're going to have some box. All right, I'm going to try to make this really pretty for you guys. We're going to have some box, and we know that it's going to be experiencing some force due to gravity. So that force is definitely going to be represented by an arrow pointing downward, and I'm going to label it as F sub G for the force due to gravity. Now, at the same time, I know that it must experience some force upward as it's resting on a table, so its forces must be balanced. And that force upward, we're going to call the normal force, and that's actually what this problem is really asking us to find. The thing is that there's also going to be some other force pulling upward on the box. That other force pulling upward is going to be equal to the force due to gravity of our counterweight. When I'm talking about the counterweight, I'm talking about, if you're looking at the picture, it's that weight on the other side of the pulley. So what we have in this problem is a simple pulley, and all that simple pulley is going to do is it's going to redirect the direction of force due to gravity from our counterweight to be facing upward and pulling up on the box. So that's going to be the purpose of the pulley in this scenario, just redirect the direction of force due to gravity for that counterweight. So if our counterweight weighs something like 30 newtons, for example, then that's going to be 30 newtons in the opposite direction of the force due to gravity. So if the force due to gravity of the box was 77 newtons, all right, then the net force downward for A, the net force downward is only going to be 77 newtons minus 30 newtons. That gives us, of course, only 47 newtons, and it's 47 newtons that our normal force is going to have to counteract to make this box balanced on the table. So for A, we would say that the answer is 47 newtons. Awesome. So for B, it's going to be very simple and similar. Our net downward force is going to be found by taking our 77 newton weight of our box and subtracting 60 newtons from it. That's going to only give us 17 newtons. In that case, our normal force is going to only be 17 newtons. All right. And then for C, this one's pretty interesting because it says that the counterweight is going to actually be greater. The weight of the counterweight is going to be greater than the weight of the box. In this case, the counterweight is going to have enough force to fully counteract gravity and cause the box to be lifted in the air. If that's the case, then what's going to happen is that we're no longer going to have to consider how much normal force the table is putting on the box, because the box no longer is making contact with the table. So we'd say that the normal force is 0. All right, happy studying, and I'll see you in the next one. Welcome back, everybody. What we have right here is the second problem in our practice set for 4-3. It says, draw the free body diagram for a basketball player just before leaving the ground on a jump and while in the air. So this is going to be two different time points for our object, which is the basketball player. So we're going to draw two different free body diagrams really quickly. All right. So when the basketball player is still on the ground, then of course the one force that's acting on it is gravity. So I'm going to go ahead and draw a square to represent our basketball player, and I'm going to show that we have an arrow downward, and I'm going to label it as force due to gravity. All right, so assuming that there's nobody currently pushing on the basketball player or touching the basketball player, then what we're going to have is just the normal force that is pointing directly upwards, countering gravity, and it should be equal to gravity. So I'm going to actually do it like this, just so that I know that in this situation that my normal force is actually equal to gravity. Now, there shouldn't be any other forces acting on the basketball player at this point. So this would be our free body diagram for A, where the box is the basketball player. For B, the moment that the basketball player leaves the ground, then they become a projectile. So I don't want anybody to be confused. Like there's still some force coming from the ground. No, the moment that the basketball player leaves the ground, all the force that they used to jump into the air is no longer acting on the basketball player. The only force acting on any projectile, period, especially if we're not considering air resistance, is the force due to gravity. So again, using a box to show my basketball player, there's only one force acting on the basketball player, and that force is going to be F sub G. So that's as simple as that. He's not on the ground, so we don't have to consider a normal force. His forces are not balanced. He is going to be accelerating towards the ground, and that's all there is to it. Good luck, and I'll see you in the next one. Welcome back, everybody. We're here with the third problem in our 4-3 practice set. It says, sketch the free body diagram of a baseball at the moment it is hit by the bat, and then also again after it has left the bat and is flying toward the outfield. All right, so I'm going to have to draw two free body diagrams for this problem because we're considering our object at two different times. So for A, let's go ahead and get started. I'm going to go ahead and I'm going to actually represent my baseball as a circle in my free body diagram. That's actually pretty accurate there. At all times, it's going to be experiencing some force due to gravity. So there's going to be a force downward, and it's going to be equal to the weight. So that's going to be F sub G downward, always. Okay. Now, also at the same time, there's going to be some probably much larger force vector acting on the baseball. And I'm going to choose an arbitrary direction because I can't say for sure what direction the bat is hitting the ball at. But I do know that it's definitely going to be greater in magnitude than the force due to gravity because it's going to cause the ball to shoot out into the air with probably some upward direction. So then I'm going to say that this is going to be the force applied. Okay, so force applied. There are different subscripts that are acceptable here. I just went ahead and put applied to make it very, very clear that this is the applied force from the bat. And those are going to be the only two forces acting on my baseball the moment it is hit by the bat. For B, it's asking us to draw a free body diagram for at some point when the ball is already flying in the air. So at this point, the ball is a projectile. And when I say the word projectile, that means that there are no outside forces acting on the ball other than the force due to gravity. So any time that I say something is a projectile, or any time that you can perceive that something is just flying in the air, especially not considering air resistance, then it must be only experiencing force due to gravity and no other forces should be acting on it. So I'm going to go ahead and use the circle again for this free body diagram, and I'm going to show that the only force acting on it is the force due to gravity. Hopefully you guys like these free body diagrams, and hopefully they are neat and pretty enough for you guys. All right, that's all there is to number 22. Good luck, happy studying, and I'll see you in the next one. Hello everybody, we're back with problem 4 in our 4-3 practice set, and this one is really fun. You're going to love me for this one. Arlene is supposed to walk across a high wire strung horizontally between two buildings that are 10 meters apart. The sag in the rope when she is at the midpoint is 10 degrees. Her mass is 50 kilograms. What is the tension in the rope at this point? All right, so one thing to understand here is that at this point in time, the forces on Arlene are balanced. So whatever her force due to gravity is, it will be balanced with some forces that are upward. You might say it's a normal force, but in this case, it's not quite the normal force because we're not standing or sitting on some rigid structure. We're standing on a rope, which is applying some force due to tension. Now, let's go ahead and draw a little bit of a free body diagram to see if we can figure out what's going on here. I'm going to say that that little dot right there is Arlene. All right. So I know that there's going to be some vertically downward force vector here. Okay, that's an ugly arrowhead. All right. Some vertically downward force vector, and that's going to be my force due to gravity. And I know right off the bat that I can actually calculate that because I'm given Arlene's mass, which is 50 kilograms. And I know I can multiply that by acceleration due to gravity, 9.8 meters per second squared. This would give me Arlene's weight, her force due to gravity. So if I put that in the calculator really quick, let's see, 50 times 9.8. That should give me, yes, 490 newtons. So F sub G, in this case, is going to be equal to 490 newtons. So whatever forces are acting in the opposite direction to gravity must equal 490 newtons. The thing is if we actually draw the trigonometry for what's going on here, so you see that there's a big triangle here. If I kind of try to sketch that out and try to understand what's happening, almost like a separate free body diagram just for the tension, right? I've kind of overemphasized this angle here. It should only be 10 degrees, even though it's not drawn to scale, but just so that we can see what's going on here. We know that in a cord or a rope or a high wire in this case, tension, whatever tension that wire is experiencing at that moment, is equal at every single point along the rope, along the cord, and it's pointing with two force vectors in both directions away from any point on this rope. So if we're going to consider this point on this rope, the point where Arlene is, then we know that there's a force vector equal to the force of tension in this direction along the rope, and there's a force vector in this direction equal to the force of tension along the rope, but in the opposite direction. All right, so these two force vectors are not completely counteracting each other, okay? Their horizontal components are canceling each other out. They're both directly in opposite directions. But their vertical components are actually both pointing upwards. What that's saying is that this rope really wants to move back up to that horizontal line, okay? This rope really wants to move back up to this horizontal line, but something's stopping it. And that something is the force due to gravity that Arlene is exerting down on that point, all right? So right now, these two vectors coming from these two tension forces are both adding together to counteract Arlene's weight. Hopefully that makes sense based off of this image. If not, you might want to run that back once or twice. But what I can say now is that because this vector, here, let me get my laser pointer, because this vector and this vector are the same, then their vertical components should be the same, especially because we know that the angle over here is also 10 degrees. All right, so what I'm saying is that these two vertical components to tension force are the same. So that means that I can do this crazy thing right here. I can say that there are two force vectors in my free body diagram that are pointing directly upwards and opposite to the force due to gravity. And I can say that they're both made up of the force of tension, but in the y direction. So F sub T, y. T is for tension, y is for the vertical direction. All right. So what's happening is I have two of them. They're both acting against gravity, and the two of them together should equal the force of gravity. So then what I can say here, and hopefully you can follow this next step, is 2 times F sub Ty must be equal to F sub G. All right. And that's actually really nice that we can say that because we know what F sub G is. I can say that F sub Ty is equal to F sub G over 2. And that is 490 newtons divided by 2, suggesting that the vertical component to a single force of tension vector must be equal to 245 newtons. And that's really great. Once we get this far, we've certainly done the hardest part. We know what the vertical component to the tension force is. All right. So if I draw an isolated right triangle to represent where the hypotenuse represents my force of tension, I know that this vertical leg must be 245. All right. And if I have at least the angle here, then I can use some right triangle trigonometry to go ahead and solve for the hypotenuse, which should give us the force of tension. So given that I have an opposite leg to the angle and the hypotenuse, I'm going to go ahead and use sine of 10 degrees, and set that equal to my opposite leg, which is 245, divided by what's going to end up being my tension force. All right, so if I do a little bit of algebra here, I can quickly rearrange to solve for tension force, and I can say that force of tension must be equal to 245 divided by sine of 10 degrees. All right, I don't have sine of 10 degrees memorized, so I'm going to go ahead and plug this in the calculator really quick. I have 245 divided by sine of 10. Make sure your calculator's in degrees here. And what I get is that F sub t must be equal to roughly 1,410.9, if we're going that many significant figures, newtons. All right, so quite a lot of tension force, especially when compared to the force due to gravity, but there you have it. This force of tension is going to be equal to the vector force going in this direction along the rope and the vector force going in this direction along the rope. All right, happy studying. This question might be one that's worth watching a couple times, but good luck, and I'll see you in the next one. Hello everybody, we're back with our fifth problem in our 4-3 practice set. This problem says that a window washer pulls herself upward using the Bucky pull-it apparatus that you see in the image. Part A is asking how hard must she pull downward to raise herself slowly at constant speed? And then part B says if she increases this force by 15%, what will her acceleration be? The last bit of information is the fact that the mass of the person plus the bucket is 72 kg. So if we know that mass is equal to 72 kg, my first instinct is to try to find the force due to gravity. So we are going to draw a free body diagram here, but I want to go ahead and know what the magnitude of force due to gravity is here. So I'm just going to plug in F sub g is equal to 72 kg times acceleration due to gravity, which is 9.8 meters per second squared. All right, so I'm going to go ahead and plug that into the calculator, and I should get 705.6 newtons. 705.6 newtons, and now we are moving forward already knowing exactly how much force gravity is going to be acting down on the person in the bucket. Cool, so I'm going to go ahead and sketch a quick free body diagram. I know that I have some force downward. Let's call it F sub g, which is going to be equal to 705.6 newtons. All right, and I also know that there's going to be some force upward, and this force is not the normal force, but it is going to be the force that's being applied by the pulley, and that force should be equal and opposite to the force downward that the window washer is applying to the other side of the pulley system. So one more time, pulleys, at least very simple pulleys like this one, all they're doing is they're taking whatever magnitude of force you're applying to one side, and they're applying that same magnitude to the other side, but in an opposite direction. So in order for the window washer in part A, to be maintaining a constant velocity, then what we're going to do is we're just going to want to have the window washer to pull herself upward with the same amount of force that gravity is pushing her downward. All right, so then we just need that force, that applied force. Okay, we're going to say F sub p. We need it to be equal to force due to gravity. So that's going to be 705.6 newtons. All right, so if the window washer applies this force and she's not moving at all, then she will continue to not move. But if the window washer was already moving at some velocity, then this much force would allow her to continue to move at that same velocity. Now, B is asking what happens if we increase by 15% on our force that we're applying to the pulley, all right? Well, first off, we need to figure out how many newtons that would mean if we took our 705.6 Newton force and increase it by 15%. So what I'm going to go ahead and do for part B over here is I'm going to take my 705.6 Newton force and I'm going to multiply it by 0.15. All right. Whether I do that by hand or I plug it into the calculator, I should get something like 105.84. 105.84. All right. And this is going to represent 15% of that force that I have that I need to that's going to represent 15% of the force that I initially applied. All right. So then I want to go ahead and tack this onto that 705.6. So I'm going to go ahead and add 705.6 back to that. All right, and that should give me a total force of 811.9 8.44 newtons. All right, so now the question is, if the window washer is applying a force of 811.44 newtons to the pulley, then what kind of acceleration is she going to experience in the bucket? So for a second free body diagram, in fact, let me go ahead and do this in red because this will be our part B free body diagram. We're still going to have that force due to gravity downward, which is still equal to that 705.6 newtons. But now we have a force going directly upward, which is going to be our applied force, and it's going to be equal to 811.44 newtons. All right, so that must mean that we have a net force that's going upward, and it's going to be the difference between these two forces. So the difference, we actually just calculated a second ago, is going to be that 105.84. So we have a net force of 105.84. And using Newton's second law, F equals ma, all right, I'm going to say that, let me move this up a little bit actually. I'm going to say that 105.84 must be equal to 72 kg times A. All right, and if I do a little bit of algebra, then I can say that A must be equal to, A must be equal to 105.84 over my mass, 72 kg. All right, let's not forget our units. We have newtons here and we have newtons here. And that should end me off with an acceleration of 1.47 meters per second squared. That will be the acceleration that our window washer will experience if they increase their force by 15% after having been in a balanced force. Good luck studying. I'll see you in the next one. Welcome back, everybody, and this is the 6th problem in our 4-3 practice set. Let's go ahead and get started. This problem says one 3.2 kilogram paint bucket is hanging by a massless cord from another 3.2 kilogram paint bucket also hanging by a massless cord. All right, you can see that in the image right here. All right. Now, part A says if the buckets are at rest, what is the tension in each cord? All right, let's go ahead and focus on part A first because I want to get this out of the way. If the buckets are at rest, then that means the forces acting on them must be balanced. But based off of this picture, we should know that there are only two forces acting on them: the tension in the cord that they're connected to and the force due to gravity. So those two forces must be canceling each other out. So it's just a matter of calculating what the force due to gravity is for the whole system and then also for the bottom bucket to find out how much tension is in each cord. So I'm going to quickly draw a free body diagram where this dot is the whole system, okay? So this dot is the whole system. That means it's going to have a mass of 6.4 kg. All right, and the reason why I want to use the mass of the whole system is I want to find the tension on that top cable, and the weight of both buckets is hanging from that top cable. All right, so if that's going to be that dot, considering the mass of the whole system, then I know that there must be some force due to gravity downward. Okay, some force due to gravity downward. That's going to be equal to the 6.4 kg mass times 9.8 meters per second squared. Meters per second squared. All right, so if I go ahead and pop that into the calculator to figure out what the weight of this whole system is, then I should get something like 62.72 newtons. So 62.72 newtons, all right? Awesome. Now, we just decided that the force of tension on that top rope must be counteracting gravity, so it's got to be the exact same and in the opposite direction. So then I can say the force sub T must be equal also to 62.72 newtons. All right, so that's going to be the case for the top rope, where this free body diagram is kind of a diagram of the whole system. Now, if we want to find out how much tension is in the bottom rope, it's going to be the exact same procedure, but in this case, we don't want to take into the account the whole system. We just want to take into account the bottom bucket because from this rope's perspective, this top bucket might as well just be the ceiling. So I'm going to draw a second free body diagram, which is going to be very similar to my first free body diagram. And this time I'm going to find the weight of just the bottom the bottom bucket, which is going to be just 3.2 kilograms for my mass. And I'm going to still multiply that by 9.8 meters per second squared. All right, that should give me something like 31.36 newtons. And if the forces on this bucket are balanced, then the force due to tension, pulling in the opposite direction, must be also equal to 31.36 newtons. All right, that is everything to be said about part A. We have discovered what is the tension on each cord when the buckets are in equilibrium. All right, so I'm going to get rid of this because we're going to need a lot of space for the next one. So part B says that if two buckets are pulled, if both of the buckets, like if this entire system is pulled upward such that it experiences an acceleration of 1.25 meters per second squared, what is the tension in each cord? All right, so it's a little bit more complicated to explain what's going on here, but the calculation is actually pretty simple. What's going to happen ultimately, and I'm telling you this as the trick to solving this mathematically pretty simply, is that this 1.25 meters per second squared acceleration is going to be added to our acceleration due to gravity, ultimately to create some force downward that will be using an acceleration of 11.05 meters per second squared. But let's talk conceptually about what's happening here. All right, so I'm going to draw a quick free body diagram that's going to represent the entire system again, so with a mass of 6.4 kilograms. All right, so this dot is going to represent the full mass of 6.4 kilograms. Now, of course, there's always force due to gravity acting on it, and we just calculated what that was. It was for the whole system, it was 62.72 newtons for our force due to gravity. But now, this time, what's going to be happening is we're also going to have some force upward. Okay, we're also going to have some force upward that is going to be equal to, sorry about that. We're going to have some force upward that is going to be equal to the mass of our bucket times 1.25. Okay, so it's going to be the mass of our bucket. So this is going to be some applied force equal to 6.4 times, and I haven't given myself enough space here. This is going to be 6.4 times 1.25. All right, that's going to be this applied force. And the thing about it is that this free body diagram isn't going to illustrate it quite well enough. Let's imagine that we have some board that our bucket is connected to. Okay, if we have some board that our bucket is connected to, then what's actually happening here is gravity is pulling this down, where the acceleration is actually being applied to the board, and it's causing both of these, like as if we're playing tug of war, to impact the tension on the rope. So the forces caused by this 6.4 times 1.25 force is going to be acting up on this end of the rope of the string, and the force due to gravity is acting downward on this end of the string. So what's happening is that those two forces, while they are opposite, they're actually both contributing equally to the tension on this cable. So F sub t is going to end up having to counteract both of them. And so that's why we say in our math, might as well just add that acceleration to the acceleration due to gravity. Even though the forces are in different directions, the force that is experienced and counteracted by the force due to tension is going to be equal to the sum of those two forces, right? So because acceleration and force is directly proportional, we can just add the accelerations and assume that the forces are going to be proportional as well. So that said, what we can then emulate is as though the downward force, and I'm not going to say force due to gravity because it's not really force due to gravity anymore. We can say that the downward force must be equal to our mass, which is 6.4 kilograms, times 11.05 meters per second squared. Okay, 11.05 meters per second squared. And that will give us exactly how much tension is going to be created in our tension force. So 6.4 times 11.05, that should give me 70.72 newtons. So then I can say that my tension force must be 70.72 newtons. All right, now we're going to basically just do the exact same thing, but with the bottom bucket, following the same procedure that we did last time. We're only going to use the mass of the bottom bucket. And so we're going to say that this force down must be equal to the 3.2 kilograms times our new 11.05 meter per second acceleration. And that should give us a force of tension that is equal to 35.36 newtons. All right. This the reason that the force that's applied by the acceleration upward adds to the gravitational force is a little bit complicated to understand, and I'll admit this isn't the prettiest picture. So if you still have concerns or would like me to do a different question like this one, maybe explaining it in a different way, please reach out to me. But good luck studying, and I'll see you in the next one. Welcome back. We're here with the 7th problem in our 4-3 practice set. This problem says that 2 snowcats in Antarctica are towing a housing unit north. All right. As shown in the figure right here, the sum of the forces, Fa and Fb, exerted on the housing unit must be going north. Like the resultant vector of Fa and Fb must be pointing north. All right. So it does tell us the magnitude of Fa, but it does not tell us the magnitude of Fb. It's asking us to go ahead and determine it. And if we look pretty closely at this free body diagram that it offers us, then what we have is the vectors coming from the housing unit being applied by these 2 snowcats. And we see that this vector is significantly longer than F sub A. So F sub B must be greater than F sub A. And that's going to be our first little clue here to suggest that these 2 forces are going to be different. They're not going to be the same. And it does give us the angles. So that's going to be a clue that we're going to probably have to do a little bit of at least right triangle trigonometry to figure out what's going on here. So I'm going to take a part of this free body diagram and I'm going to kind of like rewrite it over here. So I have the point. This point is going to go ahead and represent the housing unit. And I'm going to have some vector going off in this direction, which I know to be, or to have a magnitude of 4,500 newtons. And I'm going to label this as F sub capital A. All right. And then I'm going to go ahead and draw a second vector here, and I'm going to go ahead and stay true to the image that's given and suggest that this is F sub B, but we are not currently able to offer its magnitude. Now, I'm going to offer my y coordinate here, or my y axis here, all right? It's going to be this imaginary line that's perpendicular to what our L was over here, and we do know that our resultant vector is going to be along this line, all right? And I'm going to say it's going to be something like this, and it's going to be pointing upwards for sure. All right, so a little bit more information we're given. We're given that this is equal to 48 degrees, and then this angle right here that FB makes with the vertical line is 32 degrees. So here's what we know. If these 2 forces are causing the housing unit to move straight, parallel with the y-axis, then we must know that the horizontal components of each one of these vectors must cancel each other out. All right, the horizontal components of each one of these vectors must cancel each other out. And we have enough information to find the horizontal component of F sub A. So we have enough information to find F sub AX, or the X component of F sub A, because we have the angle that this vector makes with the vertical line, and we know its magnitude. So we can say, because we know the hypotenuse and we're looking for the opposite leg to the angle, we can say that sine of 48 degrees must be equal to our opposite leg, which we're looking for, and we're saying that it is equal to, let's go ahead and not have this equal sign right here because that's going to be throwing you off, is going to be equal to F sub AX over, so it's opposite over hypotenuse, and we know that the hypotenuse is 4,500 newtons. And if we do a little bit of math here, we can go ahead and just calculate what is sine of 48 degrees. That's not something that's immediately on the unit circle, so I'm going to pop it into my calculator really quick, make sure I'm in degrees. Sine of 48 degrees is something like 0.743. I'm going to go ahead and multiply that by my hypotenuse, 4,500 newtons. And that's going to be equal to, that's going to give us an F sub AX of 3,344 newtons, roughly. Okay, so great. We know what this horizontal component is. It is going to be 3,344 newtons for both F sub AX and F sub BX, because we just decided that we know that the horizontal components of these two vectors must be canceling each other out. And that's really powerful, because once we know one leg of, or at least one component from our force B, and we know the angle to the vertical that it makes, then we can very easily find its magnitude. All right, so if I know that F sub BX must be equal to 3,344 newtons, then I can say that sine of 32 degrees, which is the angle that force B is making with the vertical, sine of 32 degrees must be equal to that opposite over adjacent again. And I know that that opposite, that horizontal component, is 3,344 newtons over, well, it's just going to be F sub B. It's going to be the hypotenuse of this part of my free body diagram. So it's going to be F sub B. And once I solve this, that's going to give me the actual magnitude of the force being applied by that snowcat on the right. All right, so just with a little bit of algebra, I can do some rearranging and say that F sub B must be equal to 3,344 newtons divided by sine of 32. All right, and then I'm going to go ahead and plug that into my calculator, sine of 32. And that should give me about 6,311 newtons. All right, so that is answering part of our question. It's asking, determine F sub B. That's going to be the magnitude of F sub B at 32 degrees from the vertical axis. And then it's asking us to determine the magnitude of F plus A plus F plus B. So that's going to be a little bit more work, because we know that the horizontal components of these two vectors are canceling out. So that means the only components of these two vectors that are contributing to the resultant force vector are the vertical components of our vectors. So that means we're going to have to take a step back in our math and calculate what those vertical components are. It's going to be very similar to how we calculated the horizontal components, but we're going to actually have to use cosine this time. All right, so I'm going to get rid of some of this because I'm going to need a little bit of space. All right, actually, we definitely need to not forget to write down and label the magnitude of F sub B once we get that, because we're going to need that. It's going to help us to find our vertical components of each one. But then I can go ahead and get rid of the rest of this. And I can say that F sub AY, or the vertical component of the F sub A, must be equal to 4,500 newtons times cosine of 48 degrees. And we know that it's cosine because the vertical component here, this vertical component here, is going to be the adjacent side to this angle of 48 degrees. And we know the right triangle trigonometry says that cosine of theta is equal to the adjacent side over the hypotenuse side. So that's where we've found ourselves here. All right, and we're going to plug that into the calculator really quickly. So it's going to be 4,500 times cosine of 48 degrees. That should give me a vertical component of 3,011 newtons. All right, so that's my F A Y. Let's go ahead and find F B Y. All right, this one is going to be equal to the magnitude of our F sub B, 6,311. And we're going to also multiply this by cosine, but this time of 32 degrees, because that's the angle that this force makes with the vertical. All right, so I'm going to plug this in the calculator. We got 6,311 times cosine of 32. All right, that's giving me 5,352 newtons. So in order to find out what the resultant vector here is, we're just going to go ahead and just straight up add the vertical components of each one of these forces together. So that means we're going to add FAY plus FAB. That's going to be 3011 plus 5352. And just to make sure that I don't say anything wrong, I'm going to plug this into the calculator as well. And that's going to give me something like 8,363 newtons. So that's going to be the magnitude of my resultant force, or this vector right here. Let me use my pointer so you can see exactly what I'm talking about. That's going to be the magnitude of this resultant vector right here. All right, happy studying, and I'll see you guys in the next one.